We'll go ahead and begin. I wanted to let you know that we're going to have a small luncheon afterwards, and so you're welcome to join us downstairs. At No Name, we have a table arranged for 6 or 8 people. We had some folks in advance who said they wanted to attend, and so we'll do that. So I would like to take a moment to introduce our speaker who's coming to us today to speak about some of the characteristics of networking. Aditya Akela has background in traffic and monitoring and traffic. You were saying estimation and engineering, I think, is the term you're using. Given what's going on with us and how we're planning to coordinate and arrange data centers coming up, this is of particular interest. So please join me in welcoming Aditya Akela. Thanks.
Thanks. Okay, so it's a pleasure to be here. So the title of my talk is Remote Profiling of Web Servers using a technique we call mini flash crowds. And this is something we've been working on for about an year. And this is kind of a bit of a departure for me in terms of my core interests. My core interests, like Gregory had mentioned, are in traffic engineering and routing. But this is more to do with servers and data centers. And this basically started out with the question of, OK, if you look at typical servers today, what is the most constraining resource? Is it the bandwidth, or is it some component of the application infrastructure? How do you tell this? And more generally speaking, how do the different components of servers impact the response time that typical users see? So we believe that with this tool, we have some initial insights into some of these issues. And this is joint work with my student at UW-Madison, Pratap, and with folks at CMU, AT&T, and IBM. Okay, so I'm going to start with basically defining what I mean by provisioning, and just to clarify this term with other common uses. By provisioning, I basically mean configuring a web server. For example, determining how much hardware to provision, kind of how much network bandwidth to provide for the server, how much CPU processing, how to provision the backend data processing subsystem, how much memory. And also various software configuration issues, such as what server software to use, how to set the parameters, for example, the number of threads, cache size, query front end, what have you. Okay? So why is determining this configuration or determining the right way to provision these servers important? Well, optimally, you want to ensure that the right configuration for a web server is able to provide reasonably good performance to the expected clients under a broad range of operating conditions, right? So you want to make sure that when things are lightly loaded, everybody stays happy, or under certain situations where there is a sudden interest in a particular stored media file, or there's a sudden interest in a particular object in a shopping cart, and even then, the clients continue to stay happy, and they get the expected response times and so on. Now, determining this optimal configuration that works under a broad range of operating conditions is a black art. It's not really easy to do this. And so what most people do is they kind of heuristically estimate that, OK, so this is roughly how many clients I expect to come see my server. And based on these expectations, this is how much bandwidth I will provide, and this is kind of how much backend data processing and memory I will provide, and I'll just configure my server this way and hope that it works. And those that have money, the bigger websites, for example, tend to over-provision these resources or sign up with some third-party content distribution networks. Now, with these techniques, like heuristically estimating or even over-provisioning, server operators typically are left with very little sense of how exactly their server infrastructure will function when subject to some kind of a sudden overload, right? In particular, how exactly different resources or components of the server behave when subjected to a sudden increase in request volume. So these kind of sudden increases can happen due to things like flash crowds, where there's a sudden interest in a particular piece of content, or due to attacks, or even due to planned events such as like a web sale, right? And the inability to provide consistent performance under these sudden overload conditions, or at least to gracefully degrade performance under these conditions, could actually piss some clients off, and they may go to your competitor. That's not something that you necessarily like, right? So you want to continue providing reasonable service under these conditions. So it's not without hope. There are definitely some techniques today to kind of understand the server performance under these conditions. So the most common thing to do is to kind of try to replicate the server setup in offline kind of a lab setting. Have a bunch of clients over a LAN, have them make some requests, monitor the behavior of the server. But the problem with this approach is that it gives you a very broad overview of the performance of the server architecture under some kind of request volume. But it doesn't really tell you, OK, so this is the constraints that individual resources on the server have, or this is how they impact the overall response time. And the problem also is that this is an offline kind of a setup, and it's almost impossible to create all of the dependencies that you have in a live online setting in an offline world. Right? So our work is basically this approach called mini flash crowds, which is essentially a lightweight distributed profiling service, which can be used to obtain detailed information about the performance of individual server resources when subjected to sudden increase in load. Okay? So the key salient features of our approach is firstly that the server stays online. Okay? This is a live server. We are testing against a live server. We use a bunch of real clients to perform these tests. So our clients are distributed across the world, and they make a bunch of requests at this live server. We can employ this tool in a black box or a white box setting. What I mean by this is a server can just come to us and tell us, oh, I have this server. Can you test this and tell us what's happening, and give us no other information about the server. We'll be able to give you some reasonable inferences. Or the server operator could be more cooperative and tell us things about how data is organized at the server, some idea about what they are using, and that will help us fine-tune some of the observations that we can make. Okay? And it's very non-intrusive, and we care about this because we are testing against a live server. We don't want to perturb its operation in any particular way. And we really envision our tool as kind of a third-party service that is deployed across a bunch of wide area clients. And in addition to understanding the constraints of individual server components, we believe that the observations that you can get from such a tool can be used in things like determining, OK, how to shape my requests when there is a certain spurt in a certain kind of request, how to schedule my requests, or to make decisions like, OK, when to provision additional resources dynamically, and so on. But the surprising thing that we realized as we went on is that this kind of a technique is actually also useful to do debugging of the configuration. So we actually found some surprising issues in the configuration of some live servers, which helped the operators kind of fix some things in their configuration when we did these experiments. Okay, so here's kind of a quick outline of my talk. And I'm going to start with describing kind of the design goals of our approach and go over the approach in some more detail. But I want to quickly stop here and make sure that everybody understands the problem setting so far. Okay? All right. So like I said, our goal is to provide very detailed observations about the performance of individual server resources. And just to kind of more formally state this, what we want to say is statements such as the following. For a given server, a particular resource X can handle at most n requests. Sorry, this is not resources. N requests, n simultaneous requests, before clients start to see a certain t millisecond degradation in response time. Okay? Think of it the other way. What we are saying is when n clients simultaneously make a request at a particular resource, the median client or the average client starts to see a t millisecond degradation in response time. And we want to be able to say this for different resources X at the server. And like I said earlier, these are kind of the requirements of our approach. Firstly, we want to be able to isolate different resources. We want to be able to do this for different resources at the server, also software and hardware. And we want to be realistic. We want to use clients that are outside. We don't want to take the server offline. And another key requirement we have is that the approach should be tunable. For example, there could be a search engine that cares about a 50 or 100 millisecond increase in the time it took to compute the answer to a query versus a site that hosts stored media or like kernel ISOs, which doesn't really care about such a tiny increase in response. So we want, in both of these settings, to be able to give fairly accurate answers. And the key challenge in doing this is, how exactly do you isolate and study different resources, especially when you have a server in a black box setting? And even if you are able to do this, how exactly do you impose a certain amount of load on that particular resource and understand how that resource behaves. And this is challenging because you have a bunch of clients that are distributed all around the internet. It's hard to coordinate their actions. So I'm going to describe to you how we address these challenges. But first, I want to kind of give you the setup we have of our approach, and then I'll drill down into the details of how we address these challenges. Okay? So our approach is mini flash crowds, and we have a target server that we want to run our test on. We are assuming it's a black box server. We know nothing about it. This test is run by a bunch of nodes, which are controlled by a central node called the coordinator. The coordinator controls two sets of nodes, a bunch of clients, and a bunch of measurers. Before starting the mini flash crowd experiment, the coordinator does a bunch of pre-processing. I'll describe to you what this pre-processing is. And based on the information collected during pre-processing, the coordinator issues commands to a small subset of the clients and to all the measurers, following which the clients and the measurers make some requests at the target. After that, the measurers report what they saw when making these requests to the coordinator. And based on this feedback, the coordinator then decides, OK, I'm going to ask a slightly larger number of clients and the measurers to go make a request at the server. And this process continues until you make an inference. So just reiterating, the coordinator is smart. It determines how to schedule clients, what requests these clients make, and in what order they need to make the requests. And it also determines how to progress the experiment, increase the load or decrease the load, and what inferences to make. And the rest of the nodes are pretty dumb. They basically just listen to what the coordinator says. OK. So given this setup, so our first challenge was how exactly do we isolate the different resources and study the performance of individual resources. And these are the resources we are talking about. And the key kind of observation, which is kind of silly if you think about it, that we use is that when a client makes a request for a certain object at the server, depending on what object the client is requesting, some resource at the server ends up getting exercised a bit more than some other resource, right? So this is exactly the observation we use when, in a particular situation, when the coordinator asks each of its clients to request a unique tiny GIF, like a 2-byte GIF that has never been requested at all at the server, then we can assume that all of these requests are going to go to some storage subsystem, which will end up retrieving it and then serving out to the clients. And because these are all so tiny, their bandwidth footprint is going to be very tiny. And no other resource will get affected by to any large extent. Similarly, when the coordinator says, OK, all these clients go and request the same large object at the server. By large object, there could be a large stored media file. Because the same object is being requested multiple times, we can assume that caching kicks in. And once caching kicks in, the only resource that you're exercising is essentially the access bandwidth of the server. And similarly, when we make tiny queries, by tiny queries, I mean a query whose response is tiny. Again, we are isolating the impact that we make on the bandwidth, and we are kind of mainly restricting ourselves to the back-end data processing. And finally, when we have all these clients make head requests simultaneously, we are basically not touching any of the resources, just kind of probing the performance of the base HTTP provisioning at the server to some extent. So to do this, in a black box kind of a setting, what the coordinator in our setting does is, before the start of the experiment in a pre-processing stage, the coordinator simply crawls the target site and obtains a bunch of objects and queries and kind of classifies them into two categories, either small, based on the size of the object or the size of the response, or large, based on some threshold. OK? OK. So that's kind of one part of the problem, which is kind of trying to isolate different resources and study the impact on resources. But then once we were able to do this, the next question is, how exactly do we impose a certain amount of load on a particular resource? Now, one thing you may say is, OK, if all the clients made, for example, n clients were to make a certain request and impose a certain amount of load, the coordinator can just say, OK, all of you guys go and request this at the server. But if they did that, depending on the latencies between the coordinator and these clients, and the latencies between the clients and the server, the requests may arrive at very different times at the server, right? And so we no longer have any tight control on the load we impose on the server. So this also kind of gives us a natural indication to what the solution to achieving tight control over the load is. We simply look at the latencies between the coordinator and different clients and just schedule the clients in the descending order of the sum of the latencies. So the farthest client you schedule first, and the closest client you schedule last, in such a manner that all client requests arrive at exactly the same time at the server. Again, once you do that, you're able to impose a certain, with high confidence, you're able to impose a certain amount of load on the server. Okay. Now the thing to remember about this is that we are assuming that by having all clients make requests such that they arrive at the same time, the server is the load imposed on the server is basically a function of the requests made by the clients. But this, to some extent, also depends on other requests that the server is serving due to other clients that are not part of our experiment, right? But the thing is that the synchronization we achieve, the way we are able to schedule the requests, it's so tight that basically all our requests arrive at a bunch at the server. And the moment the server starts to process the first request, the others are right behind it. So we can be fairly confident that the load on the server is mostly because of our requests. Okay. So once we are able to impose a certain amount of load, the next question that comes to mind is how do you increase the load or decrease the load to observe a certain degradation in response time, and when do you conclude that there is a particular limitation at a resource? And the key thing that we realize here is that because of synchronization and how we are able to schedule requests to arrive at the server at the same time, we can also have these measurer guys make requests such that their requests arrive at the same time at the server, and then we can track the response behavior observed by the measurers to understand what is going on at the server, right? So what the coordinator does is, requests the measurers to make requests to the server at the time when a certain n clients are making requests to the server, and then observes the median increase in response time at the measurers, meaning that 50% of the measurers saw at least blah millisecond increase in response times. And that is a function of the current request volume because of our synchronization. And once that happens, if the median increase in response time is above a certain threshold t, then you conclude that, I've made some impact on a particular resource. And then you say, perhaps there is some kind of a resource limitation here. This needs further exploration. Okay? If there is if this inequality is not satisfied, meaning you haven't crossed the threshold t, you increase the load by having additional clients make the request. So that's basically it. That's the simple many flash crowd approach. So basically, what we do is in the pre-profiling stage, before the measurement starts, the coordinator, like I said, crawls the target and classifies objects into these different kinds, measures RTTs between itself and the clients and the target to do the scheduling, and then also measures the base response time for different object types to understand when the response time has increased. And once this happens, the core mini flash crowd approach itself is divided into a few different stages, where within each stage, all clients request a particular kind of object, like a unique small object or a same large object or same small query and so on. These stages are divided into epochs, where within each epoch, we have a certain number of clients make a request at the server. We start with 5 clients. And the set of clients that make a request, we call it a crowd. Okay? And we schedule measurers to monitor the performance of the server when clients are making this request. If there is an increase in response time, as I mentioned earlier, we don't immediately conclude that something went wrong. We repeat the experiment at the same load a couple of different times for accuracy. If not, we progress to the next epoch by increasing the number of clients that make the request. So we kind of gradually increase the load until we are absolutely sure that we hit the threshold. Okay? And when we are able to conclude with high accuracy that something happened, the size of the crowd at that particular time is indicative of the limitation of that resource when we saw something happen. Okay? So I'm going to move on to some kind of lab-based experiments that test various aspects of this approach. And then I'm going to describe to you some experiments that we did with live sites to understand how valuable some operators thought this approach was. So the first test we did was to understand how effective our synchronization was in the presence of wide area delays. We set up a toy server in the University of Wisconsin, which was basically running a bare bones HTTP, returning a blank page. Our clients were running on Planet Lab, and they basically sent a simple request to the server. And this graph over here basically plots the arrival times of the clients as observed at the server. Okay? So the x-axis is the clients that we scheduled. We scheduled about 45 of them. And the y-axis is the relative arrival time of the clients. And what we see is about 43 or 40 of the 45 clients all arrived within 30 milliseconds of each other. And these clients are on Planet Lab, which is kind of distributed throughout the US and some in Europe. Okay? Now, this may not seem this is kind of reasonable that we are able to get requests to arrive within such a small interval of time. But we actually did much larger scale experiments where we scheduled up to 350 requests at a commercial production site. And we were able to have all of them arrive within half a second of each other at the server. So this allows us to impose very tight control over the load.
Question?
Yeah.
Why do you need the clients on the Planet Lab? Why can't you just put some PC box that directly connect to the server and start doing all this stress testing? So
that's one of the things.
Could you repeat that question, please?
So the question was, why do you need the clients to be on the wide area? And why didn't you just have the clients be on some local area network and make? So the challenge with doing that is we won't be able to test the limitations imposed by the bandwidth, the access bandwidth to the wide area network. So if you will only be able to test the limitations imposed by the local bandwidth. Does that make sense? So we want to understand how different resources are kind of dependent on each other and what limitations each of them impose. And in a local setting, we won't be able to delineate the effect of the bandwidth. Yeah.
So why is it so difficult to synchronize if you have a GPS synchronized clock? And you just say at some point in time, which is up to like 100 nanosecond accurate, you start asking for this?
Oh, no. The problem is if you did that.
Again, the question.
So the question was, why can't you have all the clients have a synchronized clock and say, OK, at this time, make a request? Now, the delays between the clients and the target are all different, right? Some of them are very close to the target. Others are 100 milliseconds away. So if you did that,
you had a window of 500 milliseconds, half a second. So the internet is, between 50 and
I understand.
150. So.
Yeah, absolutely. And if we did what you were saying, we wouldn't get even the 500 millisecond spread of requests. Things could be arbitrarily delayed enough that,
So you didn't check. You think that it wouldn't work this way?
Actually, we did. That was our initial approach of having everybody request things at the same time. But we absolutely had no control over what load we imposed on the server. So, although this seems like, OK, it's, they're arriving within half a second of each other, that's all of the 350 requests. So 1 to 350 arrive within half a second. But 90% of those really arrive within 60 to 100 milliseconds. So that's kind of what we are looking at. And that's hard to achieve without some scheduling algorithm. Are there other questions? OK. So the second experiment we did was to understand, we were looking at the median response times of the measurers, and we want to understand how well they're tracking the server's behavior. And so what we did was that in our toy server that we set up in the university, we implemented some kind of a response time function, which is basically a function of the queue length when a particular request arrives, and we tried a few different curves. And basically what this graph shows is, this is the response time function that we implemented, the solid line, and this is as reported by the median increase in response time of the measurers, and it kind of fairly closely tracks what the ideal measurement is to some extent. Okay? So again, we did a bunch of experiments. This is just a snapshot, but it seems like this approach of waiting for about 50% of the clients to show a certain degradation seems to be fairly effective at tracking the server's behavior. So that's kind of obvious to some extent. But we wanted to also question our basic assumptions of different request types impacting specific resources and how accurately are we able to isolate the different resources. So again, we set up a toy server with a bunch of objects on it. And this was on a local LAN because we now understand the synchronization effects very well. And so in the first experiment, we had a bunch of clients run this mini flash-crowd experiment, all requesting the same large object. And as the number of clients increased, the response time increased. But what we saw was that the network usage, as reported by something like ATOP, also started to increase. And we saw that no other resource, for example, the disk didn't show any reads. There was no increase in CPU utilization, whatever. So this kind of confirms that the same large object affects the network usage. And similarly, when clients request a unique small object that has never been requested before, the number of disk reads increases. So we're impacting the disk more than anything else within the server setup. Again, this is also kind of obvious, but we wanted to check it for ourselves. Now, the interesting thing comes when we are talking about the impact we are able to make on the data processing subsystem. And to test this, we set up a server with a MySQL database. The server has a query front end. We tested with two different query front ends, fastCGI and Mongrel. And the server, simply what it does is when a client makes a request, it retrieves a certain number of entries from a database, computes the mean and standard deviation of the entries, and returns it back to the client. So what we saw was kind of a very stark so all clients were making the same query here. Okay? And there was a very stark difference in the behavior we saw due to the two front ends, query front ends. So with fastCGI, we saw that the response time kept creeping up, and it started to show a performance degradation. But alongside, the CPU utilization also started to grow up. The memory usage also started to grow up. But there was really nothing that we could see of any effect at all when we were using the other front end. And turns out what was happening was that with fastCGI, it was kind of a broken implementation where each time there was a request, fastCGI would fork a new process, and the child would inherit the parent's memory image, and the memory consumption kept growing higher and higher as we made more and more requests. So to some extent, what this tells us is that, at least in this particular case where we make small queries, it's not really clear that we are impacting a hardware resource. It may be that sometimes we observe some of the effects of the software front ends for that resource, and we can't really delineate the two things. So again, we did another experiment where we had clients make different queries to remove the effect of caching, and we used the more efficient of the two front ends. And in this case, we did see that as the number of requests increased, the CPU utilization increased, and there was no impact on other resources within the system. Okay? So in some cases, this approach is able to tell us something about the hardware resources. And in other cases, depending on what front end is used, we may be actually inferring something about the software front end, but we can't really tell the two things apart always. OK. So that's kind of a broad overview of kind of what we can infer and how effective these things are. But I quickly want to go over some limitations before describing some of the experiments we did. So the first limitation is that we don't always infer limitations of hardware resources. So when we schedule a certain number of clients and we see an increase in response time, that may happen because, for example, in the bandwidth case, when an nth client makes a bandwidth intensive request, that request kind of eats up a bandwidth from the n-1 other requests, causing all of them to show a degradation in response time. So in that case, you can say the load on the resource increased. But in other cases, the nth nth request may just be queued behind n-1 other requests. And in that case, realistically, what you're seeing is the queuing delay for the client. And when the client actually ends up getting serviced by the resource, it takes a fixed amount of time, meaning the resource is not getting overloaded by any extent. In that case, the delay actually depends on the queuing, the scheduling algorithm, how many queues there are, and all of that stuff. So we can't really tell whether the delay we are seeing is because of some scheduling and queuing going on versus whether it is actually a resource limitation that we are observing play up as an increase in response time. And the other thing which is kind of we can get from our tests on the query backend is that our observations are not necessarily fine-grained enough, meaning we are not always able to pinpoint individual resources and software. They are kind of limited to at the granularity of a subsystem, like the storage subsystem and the query subsystem, which includes the hardware and the software front end, and perhaps the access subsystem to some extent. Okay? And this is a limitation that's imposed by our black box nature. If the operators to some extent cooperated with us and gave us some other information about requests that helps us separate out these constraints, then we may be able to get much finer grained inferences from that. Okay. So what I want to describe now is a bunch of experiments that we did in kind of white box and black box settings. In the white box setting, we recruited a top 50 site, as reported by Quantcast, which is a web ranking service, was interested in this work. So they came and talked to us and said, can you run this on our site? And a couple of other universities were also interested in this. So this top 50 ranked site, this is in a black box, white box kind of a setting. We had access to the logs at the server, so we could observe how our requests arrived at the server, what resources they touched, how much background traffic there was, and so on. And we also had operator feedback, which was very valuable for us to understand how effective and valuable our approach was to them. And we tested both the production and non-production versions of the server. These host identical content, but their configurations are vastly different. Okay? And the production version of the server is actually, I think it gets about 1 billion requests a day or whatever, some really high number. But the non-production version almost saw no traffic during the time we were doing our experiments. And we had about 75 clients making multiple requests. And let me go to the measurement observations we made from running our experiment on the production and non-production servers, starting with the non-production server. So what we see is, so these numbers here basically indicate the number of clients that we scheduled at which the median response time reported by the measurers saw a 250 millisecond degradation. Okay? So for the non-production version, when we made about 40 head requests, there was a 250 millisecond degradation in response time, in the median response time. For the large object case, nothing happened. We didn't see any degradation at all. And for the small query case, the degradation happened around 90 requests. And the operators were not surprised by this. They said, we have very high bandwidth, so it's not surprising that you saw nothing. Our small query, the particular query that we were using, they said that it went through multiple stages. And one of the servers in one of the stages was a known contention point in their infrastructure. So it kind of makes sense that we are reflecting that. But they were very surprised by the fact that head requests ended up showing this kind of a pathological behavior. And they actually think this is some kind of a configuration issue, and they were still debugging it at the time I prepared these slides. They don't know what is going on. The production version of the site, we saw nothing. We were hoping to see something, but really, we upped the number of requests we made from each client to 5 in parallel. We went all the way up to 375 requests, and we really didn't see any degradation in response time. And again, this was vetted by the operator's feedback that, look, our production server is in a large data center where we have multiple servers, multiple multiprocessor servers, all working in tandem to service requests. So clearly, we were not going to see anything with this kind of a setup. Okay. So again, the operators were very interested. They said, OK, they gave us a few other queries and said, can you try this? We want to see how this part of our infrastructure works well. In the interest of time, I'll skip those results. We ran our experiments on a couple of other university servers, both located in the US. The first university saw very light traffic during our experiments, about 3 or 4 requests per second. It's a basic Apache v2 running behind a 1 gigabit per second link. The second university saw maybe 4 to 5 times higher traffic during our experiments. Again, it's some kind of an oldish Sun v240 server, again, behind a 1 gigabit per second link. Okay? So again, we had access to logs and operator feedback. So again, this was actually very interesting. This kind of tells us, to some extent, university operators are not, obviously they don't care about having the configuration that works well under a lot of different circumstances, but still there were some broken things. So in the first university, we ran a bunch of experiments. This is just one experiment that I'm showing here. When we made about 100 or 130 simultaneous requests, all 3 stages started to show a degradation in response time. Okay? In particular, what we observed was that the moment the number of requests crossed 100, the response time was about 150 milliseconds or so worse. The reason it didn't show up here is that we were using a 250 millisecond threshold. Now, this is kind of surprising that it should be so consistent across all the different resource types, right? At 100 exactly, this kind of a thing should happen. And after thinking about it a little bit, we figured out that this is some kind of a software configuration parameter issue, right? Probably some limitation on the maximum number of threads at any point in time, which really limits how many requests we can make, and kind of whatever requests you make beyond that end up getting queued. And the server operators also kind of confirmed this. They said our setup is kind of 5 years old. We haven't really bothered to change anything since we put things together in 2000. And this kind of goes back to the comment I made earlier that we can't really say whether the degradation we observe is because of some resource limitations or because of some server-side scheduling issues to some extent. Okay? But the fact that things are so consistent points to the fact that there is some software configuration parameter that's broken. In the case of the second university, bandwidth was really good. I mean, we didn't see any effect even when we went up to 150 clients. For the small query stage, about 30 simultaneous requests was enough to have the server keel over. And this actually, again, this brought back some fond memories to the university operators. They said, oh, our legacy query infrastructure, we just realized was not caching responses. Okay? And which kind of explains the degradation in performance. And for the head requests, again, about 110 requests were enough to show a degradation response time. And actually, this was interesting to them. They said that the difference between head and large object was useful for them to debug a recent anomaly that they had observed, where there was a popular video hosted on the university site, and a lot of users were requesting it. And when this was happening, there was another user who was trying to make a large download and getting frustrated, not seeing the download finish at all. And they were wondering whether it was because of some bandwidth limitation or because of the server software limitation. And the fact that the bandwidth was fairly good convinced them that this is actually going to be some kind of a request processing bottleneck at the server. So it kind of helped them understand what was going on in that case. Okay? So were there any questions until this point? OK. So those were the white box kind of a setup where we had the feedback of operators, and they said this was interesting, and they realized things that they probably didn't care about and thought didn't matter. But in addition, we also ran our approach on a bunch of servers in the wild. Realize that I said it's a non-intrusive, lightweight approach, so it gives us the ability to run it on servers without perturbing their function in any way. In particular, we kind of picked servers in different rank ranges in this quantcast, meaning servers that were ranked 1 through 1,000, servers that were ranked 1,000 through 10,000. And we picked a few in each of those categories. And our expectation was that the more popular ones would be more well-provisioned than the less popular ones. And we wanted to observe similarities and differences. And we ran these tests over a 1.5-month period, mostly during off-peak hours to kind of limit the impact of background traffic. Ideally, you would want to run multiple times and kind of make sure you get a good idea. Okay? And again, our goal was to understand resource provisioning trends and kind of validate our approach a little bit more. OK. So this is the base stage, which is the head requests run against the different servers. So the x-axis here is the different rank ranges, servers in 1 to 1,000 range, and so on. And the y-axis here shows the fraction of servers that showed a degradation, 100 millisecond degradation response time when, say, up to 20 requests were made, when up to 30 requests were made, and so on. And you kind of see an expected trend. As you go to lesser and lesser popular servers, you start to see a larger fraction of servers showing a degradation in response time, which is kind of what you would expect. In particular, for the least popular set of sites, about 45% of the sites could not handle any more than 60 simultaneous head requests before there was a performance degradation. But actually, to some extent, what we found surprising was that in the most popular category, there were about 10% of sites which could not handle any more than 40 requests before there was a 100 millisecond degradation response time. We're kind of surprised at that. We expected them to be hosted at large data centers, and we didn't expect this to happen. So this is for the next stage, where all clients make the same small query at those servers. And again, the trend is the same, but the fractions are much higher, right? So on the previous slide, the maximum was about like 45. In this case, for the least popular site, we had about 75% of the servers show a degradation response time. Kind of the query processing portion of the servers doesn't seem to be as well provisioned as the rest of the setup. But again, the thing that we were a bit surprised by is, again, there are about 20% of the servers in the most popular category which could not handle more than 40 simultaneous queries, which, we don't know what is going on because these are black box type of tests, but we didn't really expect to see this kind of a trend when we were measuring these sites. And this is the bandwidth test, where all clients request the same large object. The thing that's a bit surprising is, in the first two rank ranges, the results are fairly similar across small query and large object. Kind of you see the same number of servers showing a degradation in response time. But in the last two categories, there's no increase in the total fraction. It kind of flattens out over here, probably indicating that the most popular servers provision all their resources really well. But the less popular ones tend to pay a lot more attention to their bandwidth than to their application infrastructure itself. Maybe to some extent reflects the thinking that if I have good bandwidth, that ensures automatically good response times to some extent, which we know is not really true. Right? OK, so again, we also did some tests on startups. But the basic idea is that we obtained these startups from popular technical media, and we were hoping that these would be hosted at large data centers, and we wouldn't again see any degradation in response times, which was largely true about 58% and 44% in the two cases. Head and small query didn't show any degradation response times, but we did see that about 24% and 33% in these two classes could not handle any more than 20 requests. So they're really not prepared for a success disaster kind of a situation where all of a sudden they become popular and there are a bunch of requests at the server. Okay. So I want to spend a couple of minutes talking about some extensions of our approach. This is kind of like a V0 of our approach, and we're still working on improving this approach. The first extension that I want to talk about is this notion of how this approach can inform server operators of the vulnerability of their servers to distributed denial of service attacks. So there are kind of multiple types of attacks. There are network level floods, where there are a bunch of requests that overwhelm the bandwidth, or there are application level attacks which overwhelm the application infrastructure. And at least in the research community, different solutions have been proposed for these two classes of attacks. And the effectiveness of these solutions kind of depends on the volume of the attack. The higher the volume, typically, the more successful the approach is at thwarting the attack. So our observations basically can kind of tell you what is the most constraining resource, which solution really makes sense to protect your server, and really is that solution going to be effective? Because if your server cannot handle any more than 20 requests and it starts to keel over, then no solution can really protect you. Right? You are better off kind of figuring something out at your end in terms of provisioning it better. So the other kind of application of this thing is this notion of a staggered mini flash crowd. And the key thing here is that if you go back to our synchronization approach, we kind of enforce this very tight synchronization where we have all requests arrive at the same time. And this reflects kind of a pathological flash crowd where there's a whole lot of spurt of requests. But there may be other kind of low volume flash crowds where requests arrive in a more staggered manner, and the server may be doing OK in these low volume flash crowds, but it may actually keel over in these more synchronized flash crowds to some extent. But the thing is, because of the centralized scheduling, what we realized is that it's possible for us to schedule requests to arrive at the server in any arbitrary predefined order. Right? So it allows us to test a variety of request profiles at the server and understand the constraints of the server under different situations. Okay? That actually brings me to the end of my talk. So hopefully, I was able to convince you that this is a useful tool to understand the limitations imposed by the configuration of a server. And this is actually, it's currently running as a service on Planet Lab. And if you'd like us to test any of your servers, please get in touch with us. And we actually foresee a lot of applications to this in terms of debugging, figuring out how to design your request front ends, and so on. Okay, that's the end of my talk.
So thank you. Thank you. Everyone is going to get the standard warning we have about all talks, and that is this is being recorded for the net, and so no questions, please, that'll reveal any proprietary information. But since I have the microphone here, and I have a number of questions, I'll take advantage of the opportunity to ask you one first. And that is, when you're doing this, you've got this notion of this external stimulus with your set of machines that are testing. But how is it? It's about cause and effect. How do you presume pre-existing load, and are you presuming that it's constant?
Yeah. So we don't know what the pre-existing load is, right? Ideally, what we should have done is to test a target server at different times of the day and kind of get the best of the results, because that reflects the least loaded time of the server. But one thing we noticed when we looked at the logs when we were experimenting against the university servers was that even though there was background traffic, the way we scheduled our requests was such that all of our requests arrived in a bunch, and they kind of were able to beat out other requests and impose a particular amount of load on the server at the time we scheduled it. Okay. So there is some effect of background traffic, but it's not so predominant that it severely affects the observations that we can make.
All right, so that leads me to the next question, and that is that if you had, instead of approaching this as a black box, if you were able to do this as a white box approach, what would you change about the way that you're running these experiments? And if there are any questions, please go ahead and use the microphone in the center. That way you won't have to repeat the question.
Yeah, actually, we didn't really give too much of a thought to that. I mean, it's kind of, if you were running things in a black box, in a white box kind of a setting, then you can think of it as some kind of a root cause analysis type of a situation. So we observe something, we don't know what is going on, we kind of figure out some requests that help us tell what may be going on, make those requests, and kind of draw a flow chart of, oh, it's not this, it should be this, right? We haven't really given much thought to how we would do it in a white box setting and what kind of algorithmic way we would use to explore the space of possibilities of constraints. I don't have an answer to that. But the way we were thinking of a white box kind of a setting is less automatic than that, where the operator would tell us what to run and what he expects it to be, and we kind of tell him whether that matches what he expects, if not, what possibly could have gone wrong, right? So that's the level to which our understanding of the white box approach is, and it's a great question. We really have to think about how we would do it in a much more automatic manner.
So one question. How is it compared to the commercially available site testing companies out there, like used to be Mercury HP now and some other people in the market?
Yeah, that's a good, so perhaps you were thinking about things like Keynote also, right, to some extent? Yeah, so the thing is, you can imagine Keynote employing something like this to improve the observations that they provide. As far as I know, Keynote kind of says, okay, we'll have these clients in different cities make requests. to the index.html at a server and kind of see what response time they see and use that as a feedback to inform the server's design. But they don't, again, as far as I know, they don't give any further details of really what may have gone wrong at the server when there was a certain flood of requests, whether it was a limitation due to some application infrastructure configuration or bandwidth or whatever else. That said, there is nothing unique to our approach that prevents someone like Keynote from applying it in their setting. All they really need is this scheduler and kind of saying, OK, rather than make generic requests to the base page, we'll make these specific requests to specific resources. So,
anyone else? All right. Well, please thank me, or please join me in thanking Aditya Akala.